The main purpose of this discussion is to understand how flow is measured through PLC or DCS system. In this discussion, we'll see how flow equation is developed based on the variables like differential pressure, temperature, and or mole weight of the gas application. Using the data sheet of the flow element device, equation constant is calculated. Once equation constant is known, the flow is measured at PLC or DCS based on the variable selected. We will see how flow equation is constant calculated based on the data sheets for understanding purpose. In this sections we will see for liquid and gas applications. So let's start. Topics of discussion is flow measurement equation for liquid and this is for the gas. In plant and industry only four types of flow elements are used for measurement of the flows. One is orifice meter, Venturi meter, Anubar and pitot tube. Orifice meter, the upstream face is like this, downstream face is like this. Venturi meter, we have a throat at center which is center. The low pressure is connected and upstream pressure location is half of D from this location. And D is the inside diameter of the entry of the Venturi meter. Anubar, we have upstream face is like this, the downstream face is like this, and this is a schematic through which you can see upstream downstream phase, and this is complete set of the differential pressure arrangement for the Anubar. Pitot tube, we have upstream opening through which pressure is increases and downstream pressure, so differential pressure is measured in a pitot tube. Flow equation is different for each type of flow meter. However, the basic equation for the all type of flow meter is the same, and which is as mass flow rate in liquid is equal to coefficient of discharge into flow area into square root of 2 into differential pressure into density. Mass flow rate in the gas is equal to coefficient of discharge into gas expansion factor into flow area into square root of 2 into differential pressure into density, where gas expansion factor is taken care for gas. Further, the flow equation can be written as considering the constant factor of K. So mass flow rate for the liquid is equal to K into a square root of differential pressure into density. Volume flow rate for the liquid can be mass upon density, which is K into square root of differential pressure upon density. For the gas application, mass flow rate is K into a square root of differential pressure into density. Actual flow rate for the gas is mass upon density, which is K into square root of differential pressure upon density. And normal flow rate is equal to mass upon density at NTP, which is K into square root of differential pressure into density upon density at NTP to the power 2. Flow equation in liquid, as the density of liquid is considered constant, so flow equation is dependent of only differential pressure. So this is a machine, and discharge side one flow FT flow measuring device installed, so DP is measured from this. So mass flow rate for the liquid is Km into square root of differential pressure, and volume flow rate for the liquid is equal to Kv into square root of differential pressure, where Km is equal to equation constant for the mass flow rate and Kv is equal to equation constant for the volume flow rate. Equation constant of Km and Kv are dependent on the units of differential pressures. So what is the unit for dP? It is millibar, it is mm water column or kPa. Based on that, Km and Kb will be values of Km and Kb would be. Flow equation in liquid. The following data needs to be known for any type of flow meter for calculation of the flow equation in terms of mass flow rate and volume flow meters. So what are the data is required? One is the volumetric flow rate, we should know, which is given meter cube per hour. Operating or operating or flowing differential pressure, which is it can be mmWc, millibar or any other unit. So flowing is normally mentioned in data sheet. So flowing and operating are same. Again, operating or flowing density at flow element, which is kg per meter cube. So these three data are important for calculation of volumetric flow rate and mass flow rate of any type of flow meter. These are the data. See, we have taken an example for water case. So data taken for data sheet is volumetric flow rate Q is equal to 16.8 meter cube per hour. You can see 16.8 meter cube per hour. Operating or differential pressure dP is 2500. It is written 2500. And operating or flowing density at element RD is written as 994.9. I have not written 0.9, but it is written 994. I have written 0.9. I have not taken this mistake. So kg per meter cube. So These three data taken from data sheet of water or fish. Calculation. Volume flow rate Q is equal to kV into square root of dp. So we can kV is equal to Q upon square root of dp. So kV is equal to 16.8 upon square root of 2500, which is equal to 0.336, which is constant. So volumetric flow rate Q is equal to 0.336 into square root of dp. So above equation is implemented in PLC or DCS based on K value and differential pressure is measured at PLC or DCS. Now mass flow rate M is equal to Km into square root of dp, which is mass flow rate is equal to volume flow rate into density. So multiplied mass M is equal to 68 into 994 is equal to 16,699 kg per hour. So Km is equal to M upon square root of dp. So Km is equal to 16,699 upon square root of 2550, which is equal to 333.984 constant. So K value is 333,984. So mass flow rate M is equal to 333.984 into square root of dp. So above equation is implemented in PLC or DCS. So this is for the mass flow rate equation. This is for the volume flow rate for liquid case. Now the flow equation in the gas, as density of gas is not constant, so flow equation is dependent on differential pressure and density. So how we can written? Mass flow rate is equal to Km into square root of differential pressure into density. Volume flow rate can be Kn into square root of differential pressure into density upon density NTP to the power 2. Actual volumetric flow rate is equal to Ka into square root of differential pressure upon density, where Km is equal to equation constant for mass flow rate, Kn is equal to equation constant for normal volumetric flow rate, K is equal to equation constant for actual volumetric flow rate. Equation constant Km, Kn and Ka are dependent on units of differential pressure and density. Density is again dependent on pressure, temperature and mole weight. That means equation constant will also dependent on pressure, temperature and mole weight in addition to differential pressure. Now as we know, the density of gas at operating condition Rd can be written P into M upon Z into R into T. Density of gas at NTP Rn is equal to Pn into M upon Zn into R into Tn, where Rd is equal to operating density kg per meter cube, Rn density and NTP kg per meter cube, P is pressure at operating condition in absolute unit, T is temperature at operating condition in absolute unit, Pn is pressure at NTP, which is 1.013 bar absolute, which is equal to 1.013 into 10 to the power 5 Pascal absolute. Tn is temperature NTP, which is 0 degrees Celsius, equal to 273.15 K. M is equal to mole weight, which is kg per kilomole. Z is compressibility factor at operating condition constant. Z is compressibility factor at NTP, which is constant. R is universal gas constant 8314.5 joule per kilomole per Kelvin. Flow equation can be further expressed in terms of differential pressure, temperature and mole weight, and compressibility factor and universal gas constant. So mass flow rate is equal to Km into square root of dp into P into M upon Z into R into T. Normal volumetric flow rate is Kn is equal to square root of dp into P into R into Zn square into Tn square upon Z into R, T into M into Pn square. And actual volumetric flow rate is Ka into square root of dp into Z into R into T upon P into M. These are the again equations for pressure, differential pressure, temperature, mole weight and compressibility factor. Now we have considered three cases. Now the case number 1, where after pressure, temperature, mole weight and dp is there. So case number 1, flow equation for variables of differential pressure dp, pressure P, temperature T and mole weight M. In this case is not normally used, as molecular weight is not available to PLC or DCS. However, if the molecular weight is available in addition to differential pressure and temperature, then the below equation can be used. So mass flow rate is equal to Km into square root of dp into P into M upon T. Normal volumetric flow rate is Kn into square root of dp into P upon T into M. And actual volumetric flow rate is equal to Ka into square root of dp into T upon P into M. Case number 2, flow equation for variables of differential pressure dp, pressure P and temperature T. This is the most suitable case normally used in plant and industries, as the differential pressure and temperatures are available in PLC and DCS. So we have pressure, temperature and differential pressure. Mass flow rate Km into square root of dP into P upon T. Normal volumetric flow rate Kn is equal to square root of dP into P upon T, and actual volumetric flow rate is equal to Ka into square root of dP into T upon P. Case number 3, flow equation for variables of differential pressure dP and pressure P. Sometimes only differential pressure and pressure are available to PLC or DCS, so below equation can be used. So mass flow rate is equal to Km into square root of dP into P. Normal volumetric flow rate is equal to Kn into square root of dP into P. Actual volumetric flow rate is equal to Ka into square root of dP upon P. So we have pressure Pt and differential pressure only. The following data need to be known for any type of flow meter in any case 1, 2, 3 or any other for calculation of flow equation in terms of normal volumetric flow rate, mass flow rate, actual volumetric flow rate. Normal volumetric flow rate and mass flow rates are display purpose, but actual volumetric flow rate is used for engineering purpose, particularly for the surge control. So we will take the case number 2, pressure, temperature and differential pressure. So what are the mandatory data? One is the normal volumetric flow rate, so nm meter cube per hour is required. Operating differential pressure, any units like mm water column, millibar, kp, etc. is required. Operating pressure at flow element, any unit like bar gauge, bar absolute, kg per cm square gauge, kg per cm square absolute, etc. Operating temperature at flow element, any unit like degree Celsius, degree Fahrenheit, etc. Operating density at flow element kg per meter cube and density at NTP. So these data are required for calculation of normal volumetric flow rate, actual volumetric flow rate and mass flow rate for any type of flow measuring device. This is an example. We have data sheet for Venturi for air application. So data taken for data sheets are normal volumetric flow rate key when 19,855, it is written 19,855. Operating differential pressure dP is written 1821.746, I have written 1821.746. Operating pressure 1.95, it is 1.95 kg per cm absolute. Operating temperature 126, it is written T 126 degrees Celsius. Operating density at flow element RD, it is written 2.55, I have written, but I have to check whether it is correct or not. Density at dry air NTP is not mentioned, so that needs to be calculated. And operating compressibility factor Z is 1, which is written as Z is 1. In moist air, normal volumetric flow rate is taken from the dry air basis. This means that the density of dry air at NTP is divided from the mass flow rate to get the normal volumetric rate. This is due to the fact that density of moist air at NTP changes due to change in relative humidity as the molecular weight of the moist air changes at NTP for the different RH. So it is universally accepted that the normal volumetric flow rate of moist air is taken on the dry air basis. So we need to calculate density of dry air at NTP. So density of dry air NTP can be written as Rn is equal to Pn into m upon Zn into R into Tn. So density at of dry air at NTP is equal to 1.013 into 10 to the power 5 into 28.965. This is molecular weight for dry air upon this is Zn 0.999 into 83145 into 273.15, which is 1.293. That means density of dry air at NTP is fixed, and this is 1.293 kg per meter cube. Density of operating constant RD is P into M upon Z into R into T. So we can write density of dry at NTP 1.95 into 0.981 is multiplied to get bar. Again 10 to the pi is Pascal, then 28.965 is mole weight of dry air. Z is 1 given, then 8314.5 into 126.2 plus 273.5, which is coming 1.669. Please note that we have considered is a dry air because RH is not given. Please note that a relative humidity is not known and it is not mentioned on a data sheet. So we have considered only dry air, and mole weight of dry is taken is 28.965, just for understanding purpose. But in actual case, we need to calculate the mole weight of the moist air at particular RH, and then density of moist air needs to be calculated. Density of moist air is always less than dry air. Density shown in data sheet is 2.55 kg per meter cube, which is not correct. So we need to take the correct value of 1.669 kg per meter cube. So in actual practice, actual case, this has to be changed based on the RH. Now normal volumetric flow rate, the variable of dP, P and T. So normal volumetric flow rate Q1 is equal to Kn into square root of dP into P upon T. So Kn is equal to Q1 upon square root of dP into P upon T. So we can write Kn is equal to 19,855 into square root of 1821.746 into 1.95 upon 126 plus 273.15, which is coming as 6655.44 constant. So normal volumetric flow rate can be written as 6655.44 into square root of dP into P plus 1.033 upon T plus 273.15. Why? Because this is a kg per cm squared. Since pressure is mentioned kg per cm square, so 1.033 is added. Please note that if pressure is in another unit, then add the corresponding barometric pressure in that unit to, like, add 1.013 for bar, 101.3 for kp, etc., etc. And temperature 273.15 is added because it is a degree Celsius. So above equation is to be configured in PLC or DCS for calculation of flow in normal meter cube per hour. Mass flow rate, normal volumetric flow rate into density at NTP. So mass flow rate is equal to 19855 into 1.293 is equal to 25,677 kg per hour. So mass flow rate M is equal to Km into square root of dP into P upon T. So Km is equal to M upon square root of dP into P upon T. So Km is equal to 25,677 upon square root of 181.746 into 1.95 into 126 plus 273.1. So Km is equal to 8607.101 constant. So mass flow rate is 8607.11 into a square root of dP into P plus 1.033 upon T plus 273.15. So pressure is in kg per cm square, temperature degree in Celsius. Above equation needs to be configured in PLC DCS for calculation of flow in kg per hour. Actual flow rate, mass flow rate upon density at operating condition. Actual flow rate is equal to 25,677 upon 1.669 is equal to 15,385 upon 15,385 meter cube per hour. So actual flow rate Q is equal to K into square root of dP into T upon P. So K is equal to Q upon square root of dP into P, dP into T upon P. So K is equal to 15,385 upon square root of 181.746 into 126 plus 273.15 upon 1.95. So K is equal to 25,194 is constant. So actual flow rate is equal to 25.194 into square root of dP into T plus 273.15 upon 20 P plus 1.033. Again P in kg per cm square gauge, T is degree Celsius. So every equation is to be configured in PLC or DCS for calculation of flow in meter cube per hour. So thank you. With this I have completed today's discussion. Hope you like this. If it is so, please subscribe my channel, like it and share it. Thank you. Bye bye. See you in the next discussion.